Hello everyone, today let's take a look at QP75 where we show that root 2 is an irrational number. And we can solve this using a proof by contradiction, which basically means we assume the opposite to be true. So basically we assume that root 2 is instead a rational number, and then we find some type of contradiction or something that's wrong, and that will show that in fact root 2 is irrational. So step 1 for this proof, I assume the opposite to be true. I assume that root 2 is a rational number, which basically means it could be expressed as a ratio of two integers. So I say root 2 is equal to p over q, where p and q are integers. And since this is a fraction of integers, there's going to be a way to express it such that the greatest common divisor of p and q is 1, which basically means the fraction is in lowest terms. And you can do that with any pair of integers, right? So now we can try and find some contradiction. Basically, we can square both sides of this equation right here since we're assuming it to be true. And when we do that, I'm going to get 2 is equal to p squared on q squared. So that tells me that p squared is equal to 2 times q squared, which in turn tells me that p squared is an even number because it is divisible by 2. And we've already shown that if the square of a number is even, then that means the number itself is even. So I know that p is even, right? And since p is even, well, we know that means that we can express p as some integer multiple of 2, so 2 times k, where k is an integer. And if we plug this value in for p here, we're going to get that 2k all squared is equal to 2 times q squared. And now basically we can expand the squared term over here, and we're going to get 4k squared is equal to 2q squared. Then I can cancel a factor of 2 from each side, and then I'll get 2k squared is equal to q squared. So now this tells me that q squared is some integer multiple of 2, which in turn means that q is even as well. Okay, so now you can see the contradiction is that we assumed that the greatest common divisor of p and q is 1, right? We assumed that this fraction up here was in lowest terms. However, what we found down here is that when we assumed that, we found p to be even and q to be even. So if you're even, that means you're divisible by 2. So both q and p are divisible by 2, which means their greatest common divisor is not 1, right? It's going to be 2, which is a contradiction because we assumed it to be 1. So that contradiction right there completes the proof that root 2 is in fact irrational. That's because when we assumed it to be rational, it basically didn't make any sense, so therefore it must be irrational.